Rates of change and optimization. So we're talking about today. Okay, you guys are going to learn how to interpret the derivative in context of a real world situation, and you're also going to be able to use derivatives to find optimal solutions. Okay, so let's talk about rates of change first. Okay, now there are counterexamples out there in the real world that use that basically use this whole idea of rates of change, okay? When one quantity varies with respect to time or with respect to other things, for example, temperature. Temperature varies continuously, right? Temperature increases as the months continue throughout the year. The height of a tree varies as it grows, okay? Over time, the tree will get taller. The price of stocks and shares vary with each day's trading, okay? All of these are examples of rates of change. And the derivative, that dy over dx, gives the rate of change in y with respect to x. So y is that dependent variable, x is that independent variable. We use the derivative to tell us the rate at which something is increasing. So for example, if you had dh over dt, or h prime of t, they both mean the same thing. That is the instantaneous rate of ascent of a person on the Ferris wheel. So capital H will represent the height somebody is on the Ferris wheel at a particular time, measured in meters per second. So the derivative would be that rate in which that person is going up or coming down on the Ferris wheel at a particular time. Okay? dc over dt, or c prime of t could represent a person's rate of change of lung capacity. Right? So as you breathe, your lungs expand. So however much air they can hold at a particular time, the derivative, if there's an equation that represented that, the derivative would indicate the change of a person's lung capacity over time. Liters per second, et cetera, et cetera. Okay, now these are just examples here. I'm trying to get you that whole idea of rate of change is the derivative, and basically as your dependent variable, whatever it is, as it's changing, as time is changing, increasing, decreasing, so on and so forth. So we have an example here. We have an example. We're going to do 3 rates of change examples, and then we'll use that and we'll apply that to optimization. According to a psychologist, the ability of a child to understand spatial concepts is given by the equation A equals 1/3 square root of t, where t is the age in years and t is bounded between 5 years and 18 years. You're asked to find the rate of improvement in ability to understand spatial concepts when a child is 9 years old and when a child is 16 years old. Okay? Anytime you see rate of improvement, rate of something, it's basically talking about the rate of change. Rate of change means the derivative, okay? So if I want to find the rate of improvement in a child's ability when they're 9 years old or 16 years old, we need to find the derivative, and then we need to evaluate at those respective ages, okay? So take a moment, find the derivative of A, so find dA over dt. And then evaluate it when t is 9 and when t is 16. Don't forget that the square root can be written as a rational exponent. What you guys get for the derivative? 1 over 5 square root of t?
Oh, 6.
1 over 6 square root of t. It'll be 1/2 times 1/3. That's how we get the 1/6. And then it'll be t to the negative 1/2, but you bring it down to the denominator and you rewrite it. I suggest rewriting it because we are evaluating when t is 9 and t is 16. So when you plug in 9, you'll have 6 square root of 9. So then that equals 1 over 18. And then when you plug in 16, that's going to be 1 over 6 times the square root of 16, which is equal to 1 over 24. Okay? Very good. And so essentially what that represents is that the rate of improvement of a 9-year-old, okay, to understanding concepts is 1/18, okay? 1/18, what is this? I guess units, concepts per year, okay? 16 years old, okay? A 16-year-old, their rate of understanding is 1/24 units, concepts per year. Questions on that? Like, that's how it relates back in context of the problem.
Wait, so how did you find that dA over dt?
We use the power rule. You multiply the exponent to the constant. So that becomes 1/2 times 1/3. Then remember, you subtract 1 from your exponent. So you technically get 1/6 t to the negative 1/2. But you have to make it positive. So you bring that t down to the denominator where the 6 is. And it'll technically 1/6 t to the 1/2, where you just rewrote it as square root.
Got it.
Okay. All right. So, and again, the context of the problem, a 9-year-old's rate of understanding is 1/18 of a unit per year. And then as a 16-year-old is 1/24 unit per year. Now we have to show that dA over dt is positive for t's greater than 5, less than 18, inclusive. Comment on the significance of this result. Well, when you look at the derivative, okay, the derivative is 1/6 square root of t. I have a restriction here on my domain, right? It can't be 0 because it's in the denominator, and it can't be less than 0 either, okay? So t is always positive, okay? You know, because again, can't have 0 in the denominator, so it can't equal 0, and it can't be negative because I can't take the square root of negative, okay? Therefore, the derivative is always going to be a positive value, okay? It's always going to be a positive value. The significance of that is that, remember, derivative represents the rate of change, or in this case, the rate of improvement. The rate of being able to understand a concept is going to always what? If it's positive, that means it's going to be improving or increasing. Okay, so that's the significance of this result. Okay, I'll write that in the sentence. The ability to understand now I forgot what I think said. Is always increasing. I'll say rate is always increasing. And if you think about it, that's true. When you're younger, you're like a sponge. You soak up all this information. You know, the older you get, the bigger your brain gets, the more you're able to retain, okay? And you're learning it. You're always learning, okay? So being able to understand concept is always going to be positive. The rate at which you're learning is always going to be increasing because you're always learning, no matter how old you get. I'm still learning, and I'm twice y'all's age, okay? So now C, it says show that d2a over dt squared is less than 0 for the same bounds, and then comment on that significance, okay? Well, this indicates what? Say again?
Second derivative?
Second derivative. So go ahead and find the second derivative first, and then we'll comment on it, okay? So find the second derivative. What did you give for the second derivative?
-1/12 square root of t to the 9.
T cubed, very good. So this is our second derivative. Again, t is always positive, right? So if t is always positive, then my second derivative will be what? no matter what t value I use. It's going to be negative because no matter what t is, I'm going to multiply by 12, but it's still negative 1 over that value. So t is always positive, and the second derivative, again, is less than 0, because no matter what, I mean, and if you want to add an additional sentence, and a positive times a negative is always a negative, the second derivative will always be negative, okay? The significance of that, remember the second derivative is the derivative of the first. So that's the rate of change of the rate of us, or the rate of a child understanding material. So the significance of the derivative being negative would be what? What do you mean regressing?
You're learning less.
As you get older, your brain becomes more plastic.
Oh my gosh. I mean, it's true, but like not so much regressing, because then that means that you're not learning, right? Isn't that what regressing means?
You're learning less.
Regressing implies that you go back to something, like, or you de-evolve.
But are you still learning?
You're just learning.
You're still your rate of learning decreases. Your brain becomes more plastic.
You hear that? You heard what the terminology y'all use besides the plastic part. The rate at which you're learning is decreasing. So you're not learning as fast. You're still learning, but compared to how you were when you were 15, 16, the older you get, you're still learning, you're just not learning as fast. You know, they always say you can't teach an old dog new tricks, right? It's the same type of concepts a little bit. So even though the rate in which we're learning or we're understanding is increasing, the rate, I'm about to write this, hold on. Even though the rate, how am I trying to say this? I think I can rework this. I can rework this.
It is the rate is, yeah.
See, even though
I just think is, even though we were understanding more, the rate is decreasing.
Yeah. The main thing is that you want to make sure that you emphasize, if this were a, well, this has some problems where you have to justify. You just want to make sure that you include the fact that you're decreasing, okay? Even though we are learning at a slower rate, and I would even say, you know, that's what the second derivative represents, the rate at which you're learning, okay? You're learning at a slow rate, you are still learning, and that's where the first derivative comes into play with being greater than 0. Because the rate at which we're understanding is still increasing, it's just increasing at a slower rate. But rates of change, again, it connects that derivative to real world situations, okay? The rate at which something, dependent variable, is changing based off of an independent variable. Example 2, the cost in dollars of producing X items in the factory each day is given by the equation. So we have the equation that represents cost producing a certain number of items. Find C prime of X. That is called the marginal cost function. When you find the derivative, you are finding the marginal cost function. Let's do this one together. It is 9,500 plus X, plus 12X plus 8X raised to the 0.8 power. What is the derivative of this function?
12 plus 6.4.
Yep. So 12 plus 6.4x, okay?
Would you multiply? Would it be negative function?
Oh, there would be a thing.
Raised to the negative 0.2 power. So then this would turn into 12 plus 6.4 over x to the positive 0.2 power. Okay. Very good. Yep, this one is going to be calculated. 0.2 as an exponent.
Oh no.
All right, so we found that. So that represents our marginal cost function. Now part B says find the marginal cost when 150 items are produced and interpret this result. Well, the first part is pretty straightforward. To find the marginal cost, we just need to actually plug in 150 into our derivative. Let's plug in 150 and let's see what we get. We're not talking about money here, so how should we round? Two after the decimal. What do we get?
14.35.
Okay, so 14.35. So that will be $14.35. Okay, so what does that mean? It is the marginal cost, but remember, interpreting, that means we have to do it in context of the problem. Remember, we found the derivative. We plugged in that particular x value. It increased, okay, because it's positive, all right? So what's increasing? The cost, okay, our dependent variable is increasing when what? Okay, well remember this derivative is the rate of change, the instantaneous rate of change, okay? So when, how many items was it? When 150 items are produced, basically the rate at which the cost is occurring is increasing by this much money. So what this essentially tells you is that as you make 150 items, the amount of money it's going to cost this factory is increasing by that much per unit, okay? That's what that represents. And then it kind of also gives them an idea that, okay, well, if I make 151 items, I'm probably going to be expecting another increase of $14.35. That's what they can estimate, okay? Because according to this function, according to us plugging in 150, that's how much it was when we produced 150 items, right? So if you were the person that was over this factory, you're sitting here like, okay, well, we're going broke trying to make all these items. Do we have enough to make one more? Well, according to this, it should cost about this much to produce one more item. We only got $20. Let's do it. Let's make 151. Okay? Let's find the C of 151 minus C of 150. What does that mean? You plug into the original function. You plug 151 into your original function, and you subtract it when you plug in 150 into your original function. It was just regular C, not C prime. Find that value. Oh my goodness. What is it?
What it says they're the same.
They are the same. Okay? Undo, please. It's $14.95 as well. Okay? So clearly it is the same as B. You can't just say, oh, it's the same as B and move on. What does that mean? What does that $14.95 represent?
It's
The difference. The increase and the change.
The change.
Exchange in cost. No.
the rate of change.
That's how much it is to make another one.
That is how much it is to make another one. If you recall, and I think we did this the very first lesson when we were going over derivatives and what the whole concept was. Y'all remember average rate of change? Remember, it was your y's, the difference of your y's over the difference of your x's. Well, your x's is only 1 unit, but your numerator is the change from producing one more. So yes, this is the actual cost it takes to produce that one more item. Okay, so this one is the actual cost of producing that 151st item. So our estimate was pretty good by doing the instantaneous rate of change. Just trying to get you to think a little holistically here before we approach optimization. We're going to look at one more example. Make sure you guys have average rate of change. This will be helpful when you do have to interpret a result or explain or justify. This, like anything, this is definitely the part that you should take away from the rates of change part. What does this mean in context of the problem? Here's the last one. Kathy is using a compass to draw a circle. The arm with the needle is 8 centimeters long, and the arm with the pencil is 9 centimeters long. The angle between the arms is theta. So there's a compass. Remember, one side is the pencil, one side is the point. You open it up, that's how big your circle is going to be. So it says to write the radius of the circle to be drawn in terms of theta. How do we do that? What concept are we going to have to use to represent R in terms of theta? What part of trigonometry? What part of trig? Think back to trig. I know it was a while ago. What concept? What concept connects 9, 8, R, and theta together? Say again? The cosine rule, yes. Remember, cosine rule was used if you knew 3 sides, you can find the angle, or if you knew 2 sides and an included angle, okay? Now, granted, this has to be in terms of theta, so, oh wow, change the color in there. Let me do that. So, which one do we want to use? We want to use the fraction one or the long one? The long one, okay? Because we're looking for R, and the formula said a squared equals b squared plus c squared minus 2bc cosine A. That was the formula. So the side that we wanted to find was equal to your other 2 sides squared minus 2 times your 2 sides times the cosine of the angle opposite of the side you were trying to find, which in this case is theta. R is in terms of theta. Well, not R yet, but R squared is. How do I solve for R? Take the square root. So I need to take the square root of this. What's 9 squared?
Oh, well.
81. What's 8 squared?
64.
64. Let's use non-calculator here. What is 81 plus 64?
140.
145.
145. Then I'll have minus, what's 2 times 9 times 8? Or what's 72 times 2? 144. So this is R in terms of theta. No, I cannot take the square root of 144 and say that's a 12 because there's not a perfect square within 145. So for us to cancel that out. But there's R in terms of theta. Then it says, hence, find the rate of change in R with respect to when theta is 60 degrees. Rate of change means derivative. So I have to find dr over d theta. You have to find the derivative of this function. Well, it might be helpful if I rewrite that square root. How? Not a negative 1/2 exponent, just a 1/2. What kind?
That messed me up. I think it's sign.
What concept do I need to use here to find the derivative? Or what rule? Chain. What's the derivative of the outside?
1/2 x to the negative 1/2.
But I'm not going to write an x. I'm going to write
The whole thing.
the whole inside function. Then I need to multiply this by the derivative of the inside. What's the derivative of the inside?
144 sine.
Very good. The reason why it's 144 sine theta is because the derivative of 145 is 0. The derivative of cosine is a negative sign. And since there's already a minus there, it turns to a positive and the constant stays there. So when I take care of the negative exponent and bring it down to the denominator, I now have 144 sine theta over 2 times 145 minus 144 cosine theta to the 1/2. Can I simplify this any?
Could you remove the 2 and get 72 again?
Yep.
Rationalize it?
Mm-mm. Because remember, we wanted to find the rate of change with respect to when theta is equal to 60 degrees. So once I find my derivative, I want to evaluate this when theta is 60 degrees. Or what radian?
Pi over 3.
Let's use our calculator. Because it's probably not going to come out nice.
Oh, definitely not.
Okay? So again, we took the derivative. As you guys are working this out, this is more so for the video's sake. We took the derivative because it asks us to find the rate of change in R with respect to theta. So that meant derivative. And it says with respect to when theta is 60 degrees. So we're going to plug in 60 degrees or pi over 3. Depending on which angle you plug in, it's going to be the mode you'll need to be in. So if you did choose to plug in 60, you just have to make sure you're on degree mode. Remember, your calculator defaults back to radian when it's reset, like it will be on the day of your exam.
Dang. That would be good enough.
Yeah, can you remind us?
That would be very
Oh, yeah. All right, so what do we get?
That's very answers.
I got 7.3.
7.30 centimeters per radian if we plugged in pi over 3. If you plug in the degree, of course, you're going to get something different. You're going to get
0.4931.
0.4931, so 0.493 centimeters per degree.
Well, that's the same answer.
It is the same answer, just one is in gradients, one's in degree. Okay? So basically, this essentially represents that our radian is going to change by this many centimeters as our angle as we widen our compass to make our circle. That's what that means. Okay, so again, with the rate of change, you want to make the connection between what it actually means in context of the problem when you are finding the derivative. All right, this concept is used with optimization. Optimization is the process of finding a maximum or a minimum value of a function. The solution is often referred to as the optimal solution. Okay, if it asks you to find the optimal solution, the optimal pinnacle, highest thing you could potentially get, whatever. Okay, it's the process of finding a maximum value or a minimum value. Now, this can be done 3 different ways. Okay, this can be done using your calculator. If it happens to be a calculator type question, you are able to use your calculator, graph the original function, find maximums and minimums using the calculator features. Analytical methods, depending on the function. If it happens to be a quadratic, remember quadratics, we spend a little part of a unit on quadratics finding the vertex. Okay, things like finding the vertex of a parabola or doing other things to find maximums and minimums. And of course, the last way is through differential calculus, which we will concentrate on today. Okay, remember to find maximums and minimums, that's when we set the derivative equal to, a little louder, is when we set the first derivative equal to 0. That's how we go about finding maximums and minimums using the derivative. Okay, the one thing you have to be aware of though, and you need to be aware of this with the other methods as well, is that sometimes the maximum value, the minimum value does not always occur at the first derivative equaling 0. Okay, you need to examine your endpoints as well. So let's say that you're given an interval restriction. Remember that there are such things as global maximums and global minimums. We talked about that, all right? And so sometimes depending on the function and depending on where your endpoints are, just because the first derivative equals 0 does not mean that this is the maximum point, where, or that's not the optimal solution. It is a max, but it's not the optimal one. In this particular case, this would be that optimal solution because it is higher than the other one, okay? But, you know, in the situation like this, this would be that global minimum, that optimal minimum, because it's the lowest point on the graph on that particular interval, okay? So just be aware, anytime they decide to pop up endpoints, just kind of keep in mind, okay, I got endpoints, I need to check my endpoints just to make sure that that's not where my maximum is or my minimum is, okay?
But if they don't, it's the relatives.
If they don't, then you don't have to worry about the endpoints, because now we're talking from negative infinity to positive infinity.
And since you gotta find the word that's
Right.
Way to find like a global maximum or minimum that is global without the graph.
Without the what?
The graph, like seeing the graph.
Uh-huh. Yep, and we will do that.
or phenomenon.
Yeah, we'll do it. All right. So to find extrema, to find those maximums and minimums, remember we have our first derivative test. That's when we made the sign diagram, the number line, right? That's when we set the first derivative equal to 0. We find those critical values. That's when we put those critical values on a number line. And then we look, if it went positive to negative, that meant that we had a what? That means we have a maximum. And then if it went from negative to positive, that meant that we had a minimum. That's what we've been doing up until this point to find our maximums and minimums. That's when it came to graphing. That's when it came to finding stationary points, et cetera, okay? But there is such a thing called your second derivative test. Second derivative test does not work every time, okay? But it can be helpful in locating local maximums and minimums. Basically, what you would need to do is you would need to find your second derivative, and then you would need to evaluate the second derivative at the particular x value you found when you did the first derivative. If that value, when you plug it in to your second derivative, is less than 0, that means you have a local maximum. But if it's greater than 0, that means you have a local minimum. okay?
Yeah, 'cause
Again, the second derivative test won't always work because depending on what your original function is, if you end up taking the second derivative and you end up with 0, then the second derivative test doesn't work. You'll have to use the first derivative test, okay? But sometimes using the second derivative test is a lot easier than plugging in test points into a more complicated derivative, okay? This depends. Ready? Okay. All right. So this all plays into optimization. These are just a few steps and a few things to consider when we're doing these optimization problems. Draw a diagram. Okay? If you're given this situation and it's talking about a rectangular piece of tin, the corners are cut off and it's folded to create a three-dimensional shape, you know, maybe a diagram could help. Okay? Step 2, and this is the most important step because this is what everything is based off of. Construct a formula with the variable to be optimized. That is the most important step. Without that step, you cannot do any other step. Because if you're given a situation where you don't have the original function, you have to create it yourself. And the formula that you're creating is within the problem. It'll tell you, right? It'll say that we're trying to maximize the area of a rectangular field. Well, the formula you'll need to create is a formula for area of a rectangle. Because that's what you're trying to find the maximum of, the area of a rectangle. If it wants you to minimize the cost of producing or minimize the volume of a cylinder, well, that's the formula that you need to create. Volume of a cylinder, because that's the one that needs to be optimized. Once you create that formula, you'll do step 3. That's when you'll find the first derivative and the values of x, which make the first derivative 0. So you'll find the first derivative, you'll set it equal to 0, and you'll solve. Step 4, you will determine if you have a local maximum or minimum. This can either be done using the first derivative test or the second derivative test. Step 5, identify your optimal solutions, okay? This is where you would consider the endpoints. Because once you determine which x value produces the maximum or the minimum, depending on which thing is being optimized, you want to make sure you also test your endpoints to make sure that those are the global maximums and minimums. Lastly, which is not necessarily needed unless it asks you to justify, interpret, explain, write your answer in a sentence to make sure it specifies the question that's being asked. These are just a few steps to keep in mind when you are doing some of these optimization problems. Any questions on these steps? Because we're about to do some problems. All right, get this down. A rectangular cake dish is made by cutting out squares from the corners of a 25 by 40 rectangle of tin plate and then folding the middle to form the container. What size squares must be cut out to produce the cake dish of maximum volume? Okay. So a rectangular cake dish is made by cutting out squares from a 25 by 40 rectangular tin plate. Step 1, draw a picture. You have a rectangular tin plate that's having squares cut out of the corners, okay? So this 25 by 40 plate is having squares cut out from each side. Once you cut out those squares, you'll fold it and it creates your cake dish. Can everybody visually see this? Okay. For those who may be struggling, this is that front side folded. This is that side part folded.
Oh. So you're cutting it from the middle. You're folding.
Not from the middle. But basically, once you make those cuts and you fold, like right here, basically these parts end up becoming the sides of your tin. Okay? But the thing is that we don't know how big to cut these squares. So when we don't know something in math, what do we usually put?
X.
X.
Well, they're also square.
That's why I put X on both sides, because they're all the same, right? Because they're squares,
Mhm.
right? So now if I cut off those squares, what is my new dimension now?
25 minus 2x times 40 times 2x, or minus 2x.
Very good. 25 minus 2x. I've taken off an x from both sides. And 40 minus 2x. I've cut that off from both sides. That now represents my width and my length of my rectangular 10. What's my height?
X.
Because that's, when you make those folds, that represents the height. Okay? So in this picture, we've actually done a lot of stuff that's actually going to help us in step 2. It's going to help us in step 2. Because step 2 says to construct a formula for that's going to be optimized. It asks us what size squares are going to help us produce a cake dish of maximum volume. That right there is key. Maximum volume. The equation that we need to create is the equation for volume of a rectangular dish. What is the formula for volume of a rectangular, in this prism? It's length times width times height. That's what you guys know it to be. In context of this problem, though, what's my length? What's my width? What's my height?
40 minus 2x.
Mm-hmm.
Times 25 minus 2x.
Mm-hmm.
Times x.
And of course, I probably want to go ahead and multiply this out. So then that way I actually have my equation written as a polynomial, not necessarily as factors. So go ahead and multiply this out, the whole thing, and let's see what our equation is, because this is step 2, the most important step.
I believe so.
Okay, well, so what's my volume equation?
Well, it's 130 x squared plus 1,000.
Now you know good and well, you did that too fast.
Oh, sorry.
4x cubed.
4x cubed minus 130 x squared plus 1,000 x.
X.
Online, do you confirm?
Yep.
Awesome. So that is the equation to be optimized. So we have step 1, draw a diagram to help us visualize this. Step 2, create the formula that's going to that needs to be optimized. It said maximum volume, so that's the one that needed to be optimized. So now we'll do step 3. This is when we'll take the derivative and we will set it equal to 0. So the derivative of this will be 12x squared minus 260x plus 1,000. And we're going to set this equal to 0. Now, do realize that some of these problems are going to be calculator, non-calculator. This one just so happens to be non-calculator. So that means in order to solve this quadratic, we're going to have to, or factor. Especially if it's non-calculator, factor, and it should be able to be factored. What's the first thing you look for when you factor a quadratic? Before that. And what's the greatest common factor between 12, 260, and 1,000? That becomes 3x squared. What's 260 divided by 4?
Oh, 65.
And 1,000 divided by 4. So now you have to figure, what are those two numbers that multiply to give you a number? Add together to give you a number. Let's factor this. Factor this.
4.
So once you factor this, that'll be our factors. So x minus 5, 3x minus 50. When you set this equal to 0, 4 equal to 0 is nothing. But then you'll have x equals 5, and then you'll have x equals 50 over 3. Now, both of these answers are not your answer.
So,
One of these is the correct one of these isn't. We want the one that's going to maximize volume. So this is where we can either do the first derivative test or the second derivative test. This is step 4, okay? This is step 4. Now, I'm going to use the second derivative test because this is nothing but a polynomial function that I can take the second derivative of very easily. This becomes 24x minus 260. What I want to do is I want to evaluate this when x is equal to 5 and when x is equal to 50. And according to the second derivative test, if it's less than 0, I have a maximum. If it's greater than 0, I have a minimum. So when I plug in 5 into the second derivative, is it a positive or a negative number? It's negative. When I plug in 50 over 3, what's 8 times 50? 400. Okay. Yeah, 400 minus 260, so that's going to be a positive. 50 over 3 gives me my minimum, but 5 is the one that gives me my maximum based off of my second derivative test. So when it asked what size squares must be cut to produce a cake dish of maximum volume, the squares need to be 5 centimeters long. Okay? Now, if you're wondering, okay, well, do we need to check endpoints here? Well, the one thing that we know for sure is that x can't be no bigger than 12.5. Where did I get 12.5 from? 25 divided by 2. The shortest side over here, which is 25 minus 2x, okay, if you set that equal to 0 and solve, that lets you know like the largest that x could be. Because if you cut 12.5 and 12.5 from both sides, you don't got no three-dimensional shape anymore, okay? So if you wanted to, that would technically be an endpoint that you would want to test to make sure as well that wasn't your maximum value. But I can already tell you guys that right now, that's not the case, okay? 5 is your optimal value right there. So you doing? Questions?
Can you repeat what you said about the endpoints again? About
Yeah. So in this case, back when we got our volume equation, we probably would want to check as well to see if we have any endpoints. Clearly, x has to be greater than 0, okay? Because if it equals 0, then we're not cutting off anything. We still have a flat piece of 10, and it would have to be less than 12.5. The reason why it's 12.5 is because, again, the shortest side, which was 25 minus 2x, if you set that equal to 0 and solve, this essentially lets you know that x would have to be less than 12.5 in order for it to even produce a three-dimensional shape, okay? And so when we found 5 within this setting the first derivative equal to 0, in between this restriction, 5 is the only answer that would work. 50 over 3 is actually bigger than 12.5, isn't it? Yeah, so 50.3 wouldn't even work. If we were looking from negative infinity to infinity, it would. But inside of this cake dish, I can only go to 12.5. If you check that endpoint of 12.5, which actually you wouldn't check because that would produce no squares, it would mean basically cutting all the way through. But that's when you would want to check your endpoints before you actually decide if 5 is going to be your final answer. And you would plug that into your volume formula to see if that produces the maximum or if it's actually going to be 5 that produces the maximum. We didn't check here because it wasn't equal to 12.5. So it wasn't going to be that wasn't going to be the maximum. Okay.
Yep.
All right, let's look at the next one. I have two more. I don't know how far we'll be able to get, but let's do this one for sure. Infinitely many rectangles can be inscribed inside of a semicircle with a diameter of 20 centimeters. Who's not on mute? All right. So inscribed means that it's inside of this particular semicircle, and it's infinitely many rectangles can be inscribed in it. Okay, here's just one. Okay, but realize that another one could be, you know, like this one. Okay, there's so many that could be inside of this semicircle. Okay, infinitely many. All right, but for the sake of not confusing anyone, we're just gonna stick with the black one. All right, we want to find the shape of the largest rectangle that can be inscribed, or in other words, the dimensions, essentially. Okay, the largest one.
We're talking about area?
Yeah. Okay, so there's our picture. Now let's create our equation. Let's create our equation. How can we find the area of this rectangle?
I don't know.
But we don't know any dimensions. Throw in some X's. Okay, where should I throw in some X's at?
It's not far.
And we got that far. Okay.
Or you can do like, read that for the big sides.
Yeah.
It'd be like 20 minus 2. Well,
Where are you getting 2 from?
Well, I just like, no, give me a second.
Like these little parts of the thing.
It'd just be 20 minus like X.
Technically, that has to be 10, right?
Yeah, the corners.
Okay, so from the center of the circle to the corner, it has to be 10. Okay, because that is a radius. Concept still applies. Okay, good.
Yeah.
Can we use the sector, the area of the sector for this?
We don't know the angle here, so we wouldn't be able to use area of sector. But y'all one of y'all said something. You said something about, what was that? Like I thought one of y'all did this.
Well, like, I just meant, like, on either side of the rectangle, there's area, and if you add those two together, and you subtract that from 20, that gets you the big, there's probably a better way of writing that.
So you're saying that this is
It gets you the length.
that, and then add another one that's the exact same
No,
length.
like, I was saying on the outside.
Oh, on the outside.
I
Or
think this
you
is
can
what
just do
we're supposed
20
to do.
minus X, and X would be the whole of the rectangle.
20 minus 2x, and that would be the length of the rectangle.
Oh, I see. Okay. So you're basically saying, this will be X, and then that will be whatever's left over. Okay. Interesting. All
Is
right.
that what we're supposed to do?
Huh?
Is that what we're supposed to do?
I think this might be an easier route if you do it this way. So remember, focus on the fact that you're dealing with the rectangle. You're trying to create the area equation for the rectangle. Okay? The only rectangles. What's this angle down here?
90.
It's a 90-degree angle. Okay.
External trigonometry.
Huh? 2x squared equals 2x squared. 2x squared equals 10. Where'd you get that from?
The hypotenuse is 10. It's supposed to be
Wouldn't it just be?
But then you're assuming that.
That's because that's.
You're
does that
assuming they're
also be
equal.
X?
But you're assuming that they're equal.
Not.
They're not equal. But we do know something. Area is supposed to be length times width of this rectangle, right? Well, I know that my length Can I make the bottom my length? So I already know it. That is going to be 2x. Because if this is x, then we double it and we'll get the full thing, right? Now we just need to figure out width. Okay? But maybe there's a way that we can.
Oh, can you figure out the length in terms of?
You can figure out the width in terms of.
And you just plug that into like Pythagorean theorem, get big, like it'd be the width plus the width squared plus x squared equals 100.
Exactly.
Okay.
The width squared plus my length squared is supposed to equal my hypotenuse squared, which is 10 squared. This will give me w plus x squared equals 100. If you can rewrite it so that it's in terms of another variable, then you will be able to get.
Would it be subtracting it?
It would be, thank you.
Okay.
And we're about to have a whole wrong problem. Did you not caught that? Now we're able to actually substitute that in for our width. And now it's in terms of one variable. There's my equation. There's my formula that I'll need to optimize. That's step 2. So we had step 1, which was creating the picture and getting all the pieces in there. And again, we did the Pythagorean theorem because by us making part of the rectangle, half of the rectangle, one variable, and then making the other side a different variable, we're able to connect them using Pythagorean theorem that was plugged in to get our area equation. That was step 2. Now we're able to do step 3, and that is where we take the derivative of area with respect to x. What rule am I going to have to use here to do the derivative? Product and chain. Yes, yes, yes. So, it's going to be the first times the derivative of the second. That's 1/2 100 minus x squared to the negative 1/2 times the negative 2x plus the second times the derivative of the first. The derivative of 2x is just 2. When I multiply my pieces together, 2x times 1/2 times a negative 2x becomes a negative 2x squared. This 100 minus x squared to the positive 1/2 comes to the denominator. And then I have a 2 square root of 100 minus x squared as my derivative. I need to set this equal to 0 and solve, okay? I'm gonna swing this right on over here. And I'm gonna solve for x. So this becomes 2x squared over the square root of 100 minus x squared equals 2 square root 100 minus x squared. Did everybody see that? Because it was a minus 2x squared. So I added it to the other side. I'm going to multiply both sides by the square root of 100 minus x squared. What happens when I multiply the same square root by itself?
It just becomes what's inside. Then you just-
So I distribute over the 2. Bring over the negative 2x by adding. Dividing both sides by 4. And x is equal to plus or minus 5 square root of 2. Now, first off, only one of these makes sense. Which one? The positive, because it's supposed to represent the length of a rectangle. And can I have a negative length? I cannot. Okay? So, let's just make sure this does, the positive value does give us a maximum. Now, I'm definitely not going to do the second derivative test here because now I got to do quotient and chain, and no, I'm not doing that. So I'm going to do the first derivative test. I am going to plug in 1 and probably 8. Those are two values that are to the left and the right. I chose 1 because it's bigger than 0. X cannot equal 0, but it's definitely less than 5 root 2. And I chose 8 because the square root of 50 is 1 bigger than the square root of 49, which is 7. So I know that 8 is on the right side of 5 square root of 2. I'm going to plug it into the derivative to see if I get a positive or a negative, just to be sure. Now, you're more than welcome to say it's 5 square root of 2. I'm just going to give it a guide and go. Okay? But when I plug in 1, that's going to give me a negative number, a negative 2 over 10, plus almost 20. So that's going to give me a positive number. And when I plug in 8, that will give me a negative number, because this will give me a negative large number plus a smaller number, because 8 squared is 64 times negative 2. Yeah. That's a minimum. Say again?
That doesn't look like a maximum.
What do you mean? You want to test it
No,
out?
no. I was thinking second derivative.
No, definitely not second derivative here. Straight first derivative test. So find the shape of the largest rectangle that can be inscribed. Well, to produce that largest area, x, it's going to have to be 5 square root of 2, which means that my entire length, let's do this in red. The entire length of my rectangle is going to have to be how long? Say again? It's going to have to be 10 square root of 2 centimeters by how many centimeters? Let's plug it into W. That's going to be 100 minus 10 root 2 squared. Oh, I'm sorry, not 10 root 2. I'm sorry. 5 root 2.
Yes.
So it's going to be the square root of 50. Yeah, I'll plug my x value into W to find that width. And so that's going to have to be the dimensions of my rectangle, so that it gives me the largest rectangle that can be inscribed inside of a semicircle with a diameter of 20. So with optimization, you want to make sure that you create the equation that's going to be optimized. In this case, it was the largest area, so that was our area formula we had to create. Same thing with the last one. It won't always be area, And sometimes you won't have to create your own equation. It'll be given to you, okay? But once you do that, you want to find the derivative and set it equal to 0 to find out if that value is going to indeed be the optimal solution or not, using first derivative or second derivative test. And then from there, of course, you make sure that it makes sense in context of your problem, as always. Questions?